What's up, guys? Welcome to Math Walkthroughs with Mr. Weeb. Today we're looking at exponential notation. Our first question says, tell what each power means, but don't determine its value. So when we look at 5 to the power of 3, that's the same as saying 5 times 5 times 5. It's repeated multiplication. So when we see 2 to the power of 6, it simply means 2 times 2 times 2 times 2, 6 times. And there you go. All right, next we've got determine the value of each power. I am going to use my calculator for some of these, but I don't think I'll need to for the first one. 1 to the power of 5 is like saying 1 times 1 times 1 times 1 times 1. And 1 times anything is just itself. So when I say 1 times 1, I'm just going to get 1. Even if I'm doing it multiple times, I'm still going to get 1 at the end. When I plug in 4 to the power of 7 in my calculator, I end up with 16,384. And when I plug in 3 to the power of 10 on my calculator, I get 59,049. And then question 3 asks, why might someone predict that 4 to the power of 10 would be much bigger than 10 to the power of 4? Well, we can see that when we looked at these last couple of questions, this one here, 4 to the power of 7, was actually much, much smaller than 3 to the power of 10. Even though our base is smaller, when we had a larger exponent, we can see that it made for a much larger value. So I might say something like this. Oftentimes, the exponent makes a much bigger difference on the value than the base. Let's move on to question 4. Question 4 asks us, how would you convince someone that x to the power of 3 could be a lot more than x to the power of 2, but it could also be only a little more than, or even the same as, x to the power of 2? Well, let's start with a very, very small value. In fact, the smallest value for x that we possibly could. What if we had a value of 0 to the power of 2? Well, now our factors are just 0. This means 0 times 0, which is going to be 0. And 0 to the power of 3 is going to be the same. It's still going to be 0, no matter how many times we multiply something by 0. In a similar fashion, if we have our base of 1, we have 1 times 1, which is 1. Or if we cube it and say 1 to the power of 3, we're still going to get a value of 1. Now, if we change our values to something very, very large, let's say we're doing, let's say if x is 100, okay? Now we have 100 to the power of 2, and this will give us 10,000. And an easy way to do that is just taking 100 times 100, and you just have 4 zeros. You take those zeros in 100, and you just put a 1 with 4 zeros behind it, and there you go. If we have 100 to the power of 3, we're going to get a much bigger number. Now we have a 1 with 6 zeros behind it, which is 1,000,000. 1,000,000 is much, much bigger than 10,000. So we can see we've already proven that x to the power of 3 could be a lot more than x to the power of 2. But it could also be the same as x to the power of 2, as we've proven in blue over here. And it could also be just a little bit. Let's take a smaller number. Let's take 2 as our base. All right? Let's say we have 2 as our base, and we do to the power of 2. That's going to be 4. 2 to the power of 3, 2 times 2 is 4, times 2 again is going to be 8. So you can see now that 2 to the power of 3 here is just a little bit more than 2 to the power of 2, rather than being the same as when we use 0 or 1 as our base, or being much, much more in the case of 100. Let's move on to question 5. Here we have, which of these powers does not describe the number 1024? Okay, well, here we can just punch it into our, we could just punch it into our calculator, but I think we can already tell here that D does not work, right? Because 10 to 1024 to the power of 1 is 1024. If we punch into our calculator 32 times 32, well, let's go 4 to the power of 5. 4 to the power of 5, well, that's 20. That equals 10. That equals 1024, so it can't be that one. 32 squared, or 32 to the power of 2, is 1024, so it can't be that one. So it has to be C. All right, that's it for today. Thanks for watching.